Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
What if I told you that the same basic element found in ordinary sand can be transformed into a material that seals skyscrapers, protects electronics, lubricates machines, survives engine heat, and even becomes medical-grade tubing? And here is the surprising answer. Silicone is not simply melted sand. In fact, the factory first breaks down silica at temperatures that can reach around 1,300 to 2,000 degrees Celsius, turns it into silicon metal, then chemically rebuilds it into flexible silicon-oxygen polymer chains. That is the real magic. Not melting, but molecular reconstruction. To understand silicone, we must first clear up three similar-sounding words. Silica is silicon dioxide, SiO2, commonly found in quartz and sand. Silicon is the elemental metal-like material extracted from silica. Silicone is the final polymer, made of silicon, oxygen, carbon, and hydrogen. Silicone polymers are not ordinary plastic. Their backbone is not mainly carbon-carbon like polyethylene or PVC. Instead, silicones are built around a repeating silicon-oxygen chain, called a siloxane backbone. Organic groups like methyl, vinyl, phenyl, or hydrogen are attached to the silicon atoms, giving silicone its special flexibility and stability. The journey begins with quartz, quartzite, or high silica sand. But factories do not simply use any beach sand. The raw material must have high silica content and controlled impurities. The quartz is first crushed, screened, and sized. Oversized pieces go back to the crusher. Then the silica is blended with carbon materials, usually coke, coal, charcoal, petroleum coke, or wood chips. These are not just fuels. They are chemical reducing agents. Their job is to remove oxygen from silicon dioxide. The simplified reaction is silicon dioxide plus carbon yields silicon plus carbon monoxide. Inside the electric arc furnace, massive graphite electrodes descend into the furnace charge. Electrical energy passes through the carbon-rich bed, producing intense heat. Temperatures inside silicon production furnaces can reach up to 2,000 degrees Celsius, with the hottest zone near the electrode tip. At these temperatures, silica loses oxygen, carbon becomes carbon monoxide gas, and molten silicon collects near the bottom. When the batch is ready, the furnace is tapped. Glowing silicon flows out like liquid metal. Now the factory enters the real chemistry of silicone. The powdered silicon is reacted with chloromethane gas. This industrial route is known as the Miller-Rochow process, or direct synthesis, occurring around 250 to 300 degrees Celsius. The key product is dimethylchlorosilane, one of the most important building blocks for silicone polymers. The methylchlorosilane mixture now enters distillation columns. Here, molecules are separated by boiling point. Think of this step as molecular sorting. One stream may become silicone rubber, another silicone fluid or resin. Now comes one of the most important steps, removing chlorine and building the silicon-oxygen chain. Methylchlorosilanes are reacted by hydrolysis. This creates siloxanes, molecules with alternating silicon and oxygen atoms. Siloxanes are now polymerized. In this step, small molecules are converted into long, stable polymer chains. By controlling chain length, engineers can produce everything from low-viscosity fluids to tough elastomers. Pure silicone polymer alone is not always ready. The factory adds fillers, pigments, and catalysts to tailor its properties. This is where silicone becomes a tailor-made engineering material for specific industrial applications. Now the compounded silicone is shaped. Liquid silicone rubber is mixed and injected into heated molds to cure. Why does silicone survive where many plastics fail? The answer is its unique molecular architecture. The silicon-oxygen backbone is much more thermally stable than carbon-based polymers, resisting heat, cold, and UV. Before it leaves the factory, every batch must pass strict quality checks for hardness, strength, and thermal stability. So the factory is taking one of Earth's most common elements and rebuilding it into one of the most versatile materials in the modern world. From sand to performance, that is the hidden chemistry of silicone. Thanks for watching.